see that when we were defining random variable, we introduced two sets. One set is named as domain, and there's a corresponding set such that each element of domain is mapped onto, and name of this corresponding set is codomain, not range. And range is a subset of it, or image. So all these elements inside this domain under this function random variable must be mapped onto some elements inside the range, but not necessarily to other elements is not included by this range. So somehow the name got switched yesterday when I was explaining. I said that the outer and bigger set is range and the inner and smaller one is a codomain, but that's wrong. You should switch those names. The bigger set is called codomain, and smaller set inside is the range. My apology. So given this definition, we further move on and introduce two very important notions today. First one is a discrete random variables case, probably mass function. Nothing but the density function in the case of discrete random variable. So name is PMF. Just take the initial from these three different words. Probability mass function. It just shows that how likely those outcomes that are possible under this random variable x. So introduce certain random variable x. That's a function which is defined over the board. So discrete on top of it, not just a continuous, a discrete. The values that can be taken by this x is countable. And then the corresponding probability is summarized by this function, so-called the probability mass function. And notation for this is a lowercase p. It's different from the uppercase p. Uppercase p represents probability measure. Lowercase p is the notation for this probability mass function. So what it says, the bigger x, which is random variable x, might be take on this value little x, so this is some number, and there's a certain probability of that happening, and that probability is denoted by this lowercase p. That's a probability, this specific probability. The value should be 1/6 because it's a fair die. Each one of those outcomes are equally likely. So that's a probability mass. The name slightly changes if we move to continuous case, and if the random variable becomes continuous, this middle word, the mass, changes to density, probability density function. But in the case of a discrete one, we just stick with this name, so-called the probability mass function. It just refers to us how likely those outcomes are. Two important properties of this function. All these values must be non-negative because it's a probability after all. This is how likely those outcomes are, so it cannot or should not be any negative number. Should be at worst 0, which never happens, or some probability, positive probability, that's likely to happen. How likely that those things are to happen. Since again it's a probability, and if you exhaust all those potential and possible outcomes by x, those added probability must be summed to 1. So each one of these little p represent different probabilities for different x's, and if you count them all, include all those possible outcomes and figure out all those corresponding probabilities and add them all up, those added number must be sum up to 1 because you basically exhausted all those potential outcomes. As long as these two conditions are met, that's a valid PMF function, and we can construct them for different cases. Equally likely, equally important, but somewhat different definition, which is a cumulative distribution function. This is a lot more sophisticated, actually. It's built on this PMF, but definition changes. It's just not the probability at x equals some number x. It's either equal to or less than. So the big difference between definition for the previous one, PMF, is just strict equality. You only consider the case that this x becomes little x. But for CDF, which is a cumulative distribution function, simply abbreviated as C dot D dot F dot, you accumulate everything up to this x. Not just x equals x, and any other x is less than x should be included. So for example, x can be three different numbers. Possible outcomes are three, either 1, 2, or 3. If you write down the PMF and plug in a number 3 in it because that's one of the possible outcomes, it's just a probability such that x specifically be this point. But instead, if you put the same number into CDF, which is a cumulative distribution function, that is still probability. Notation is big F. But not just this probability, and anything less than that should be included as well. So this inequality is the only difference between what we define under this PMF and what we are now defining under this CDF function. Cumulative, you have to add up all those probabilities up to this point, not just at this point. Anything before should be included by this one. So that's a bigger number. And notation for the second function is this uppercase f. So from now on, if you see this uppercase f of some variable in it or number in it, you automatically think of this CDF function, cumulative distribution function. The first name explains everything well. Cumulative because you have to accumulate all those different probabilities all the way up to this specific choice of little x. Not just that x, anything before should be included as well. So they are related because the second definition, CDF, is based on this first PMF. You see the PMF inside, that becomes the sum end. But the difference between the previous PMF and this now CDF is that you have to sum them all up. This part is new. And so we will practice on how you can move from one to another. Usually constructing the CDF, second function based on the first one, is more straightforward. But moving the opposite direction, given the CDF function, coming up with this PMF is more delicate, but not that difficult. So one of those likely candidates for the exam. I provide you guys with some CDF function of certain random variable like this one, and then ask you to construct the corresponding PMF. Go back to the first one. That's one way to check your understanding, how well you understand the connection between this PMF and CDF. A few important properties about this CDF function. First one, why do we bother to compute this one? Why do we bother to define this one? Because it can be used to figure out certain probability. So say that there's a variable x, and you might want to compute the probability such that this x, discrete random variable, either bigger or equal to some number little a, but has to be bounded, upper limit of little b, which is bigger number. How do you compute this probability? You can depend on the CDF function. First, evaluate this function at the right end point, which is bigger number, bigger end, b, and then subtract the same function, but evaluate it at different point, and that different point, second point, is a minus. And this is not a typo. And that means immediately next to it, but on the left hand side. So if I explain this on board, I'll draw a real line and pick any random number on it. Could be like a, some number. You approach this a from the right hand side and stop just before this. Not exactly the same as a, but extremely close. And that's a plus. So just stop right there. Almost there, but not quite so. And that's a plus. But if you do the same thing, moving from left to the right, that becomes a minus. Now you move from left to the right. Again, exactly the immediately before you reach this a, you just stop. And that's a minus. And that's the same a minus that we are having here. So to speak, a minus epsilon or something. Very tiny fraction. Very tiny number. So then what's being claimed here, probability for this interval x, you first evaluate the CDF at the right endpoint, which is B, and then subtract the CDF evaluated at A minus instead of A. What happens if you drop this one, drop this sign, and go ahead and check the difference between f of B and f of A? What are we computing? Given that the CDF is all the probabilities up to that point. So the only reason why you have to put this minus on top of this A is because you want to keep this equality. But if you drop this one for some reason, what happens? Yeah, exactly. You have to drop this equality. If you delete this one and then delete this minus, then equality is preserved. Right? So what's being said, and what she said, you still want to keep the equality, but then you have to drop this equality on the left hand side. Then these two things become exactly the same. The reason is because if you write it this way, this probability here, which is cumulative, must include this probability. Because this one includes everything up to A. So P of x equals A must be in this one, but you are subtracting it. So you're ruling out the possibility that x becomes A. So you have to drop this equality, then it becomes the same. They become the same. But if you want to keep this equality on the left hand side here, you have to rule out that possibility of including A in it, and the only way you can do it is just to drop it. Just stop right before A. Before you reach it, you stop, then that event, x becomes A, won't be included by the CDF evaluated at A minus. Strictly because of this definition. Because of this definition, you see the equality here. Once you put certain number inside this CDF, probability that x becomes that the same x must be included. So if you subtract that one, you have to drop the equality, possibility that x becomes A too. But if you still want to keep it, you just don't include that specific point A. And how you drop it, just replace A by A just to short of something just short of A. Then you'll be fine. For the exact same reason, if A is an integer, if you evaluate the CDF of x at A minus, something extremely close to A but not exactly the same, just stop a little short of it. It's just the same thing. Evaluate the same CDF function at A minus 1 because A is just simply integer. So what is being said, A could be like a number 3. That's just the integer. And if you want to evaluate this probability mass, not probability, CDF at something just short of 3, not exactly the same, which is 3 minus. And if you compute the CDF of that at this point, it's just the same thing as computing all the probability up to 2 and then just add them all up because there's nothing in between. Whether you stop here, stop here, stop here, it's just the same thing. It's just the same as the probability CDF at A minus 1 because A is just simply integers. But if you drop this minus at the top of this A, then of course these two CDF values will be different because you are excluding the probability mass around this x equals A by just plugging in A minus 1 into it. So if you want to keep this, preserve this equality, you have to replace this A by A minus such that the probability mass around that x equals A won't be included. So they're like discrete time points or whatever the value might be. Some probability mass around here, nothing in between. You have the second probability mass here, nothing in between. There's a third object, you have another probability mass around there. If you stop in the middle of it, it's just the same thing as you stop one before, because of the way we define the CDF function and everything. If you try examples, the picture will get a lot more clear. First one, coin tossing. We did it yesterday. In fact, just introduced it under the random variable rather than the CDF and PMF, but we do it under the PMF here. So define X to be the required number of trials until you get the first head. Just keep tossing the fair coin, either heads or tail, and you stop if you have the first head. That's the thing that you try. Probability mass function. Assume that the required number of trials takes on the value little x. Little x could be 100, or could be 200. Relating probability for this outcome, the fact that you stopped at the xth trial, which means that the previous x minus 1 trials are all failures, all tails. And probability for that is this. Each independent trials and events, each one of them, there's a success probability of P and probability of failure, tail, 1 minus P, and you just have to repeat it as many as x minus 1. So that's this probability, highlighted one. But then when you come back around and try one more time, which is the xth trial, you finally have the first success with a probability of P. That's another independent event. So putting them all together, probability that you stopped at the xth trial is nothing but this. First, x minus 1 fail. So each failure occurs with a probability of 1 minus P. Repeat it as many as x minus 1 times, that's this. And then finally, you finish up with multiplying that thing by P. Success. At last, when you try one more time. So that's the actual probability for having this. Otherwise, it's nothing. So that's a PMF. And this specific PMF has a name. It's called a geometric distribution. This name must sound familiar. Where did you hear this geometric thing? Geometric series. High school algebra. Start with the initial value. Multiply that value by some number less than 1 but bigger than 0. Becomes AR. Second entry, multiply the same R to the second entry, the third one I mean. And all the way to the infinity. If you add them all up, you get some fraction. What do you write at the top? Initial value. And what about the bottom one? 1 minus the common factor. And name for this kind of series is called a geometric series. Same thing. Initial value of 1 minus P, you just, well actually the P, and then you keep multiplying by the 1 minus P all the way to wherever, whenever, and how far you want to go. That's a geometric distribution because it's a random distribution rather than just non-stochastic and non-random. Some other examples. Utilizing these notions of PMF and CDF. There's an automobile service facility. They specialize in engine tune-up. They fix up the engines so that they can make some noises. From their past history, this owner of this facility knows that 45% of all tune-ups will be done on the 4-cylinder cars. Another 40% will be on the 6-cylinder ones. And the rest of them, 15% will be the 8-cylinder automobiles. Has to be one of those four. Either 4 cylinders, 6 cylinders, or 8 cylinders. I haven't heard anything bigger than 8 or less than 4. Has to be one of these three cases. They're exhaustive. Given this, define random variable x such that it means the number of cylinders on the next car to be tuned. First question, write down the probability mass function of this. So PMF is simple to construct. List all those values that can be taken by x, and then fill in those blanks by figuring out what's the corresponding probability for each. and then you are done. So it's a very simple case. So if you do it together, you should write something like so. Cannot be simpler than that. So list out those possible values by x, taken by x, either 4, 6, or 8, and for each the corresponding probability, 45% chance for the smallest number of cylinder car, and then the middle one, 40%, and the last one comes with a probability of 15%, or 0.15. A few things to check before we move over. If this is a valid PMF, if you add up these all possible probabilities, they must be 1, which is indeed the case here. So you know that you're on the right track. Well, you can use the graph to present the exact same information instead of table. Raise the height of the bar up to the level of probability, and those 3 different bars for those 3 different values that can be taken by x and carries the exact same information as the previous table. It's just a different form, graph. Will this be on the exam? Of course not. It's way too simple. Third one. By the way, this quiz performance is better than I expected before, so I think I'll make the second quiz harder. Because I mean, if everybody gets 4, there's no differentiating factor. I mean, I want to see some distribution. Hard workers do better, and then people who didn't do work much, didn't have much work done, and get less. I'll see. I mean, just make it slightly harder, and then see how it goes. And if there's some distribution, I'll just fix the difficulty level there. If it's not enough, I'll raise the bar further, and so on. Next one, under the same issue, computing some probabilities using this PMF. First event that we need to compute the probability for, next car tuned has at least 6 cylinders. So there are possibly 4, 6, and 8, and at least 6. So keyword in computing this probability is this one, at least. It means that either 6 or 8. So figure out each probability and add them up. That should be the right answer. And more than 6 only leave you the choice of 8, because you have to exclude a case the number of cylinders is 6. The only remaining choice is 8 cylinder ones. So using the table or graph that we just constructed, so these probabilities can be easily figured out. It should be this. If it's at least 6, it can be either 6 or 8, and each corresponding probability for the x equals 6 is 0.4, and that for x equals 8 is 0.15. Add them up, I will give you the answer of 0.55. Secondly, it's just the case of x equals 8, because it has to be strictly bigger than 6, and that's only just the case of these 8 cylinder ones, and the probability for that one is a 0.15. It's more like a warm-up. We try slightly more challenging one for the next example, but for now that's enough. Next one, the opposite. Instead of given the PMF, you now given the CDF. This is how the CDF looks. So notation for any CDF is big F, and it basically breaks up those entire range of x into sub-intervals and give for each intervals relating cumulative distribution function value. So given this CDF, cumulative distribution function, you have to construct PMF. That's the question. So given this CDF, you are supposed to construct a similar table that you just write down. How do you do it? So in constructing the PMF, always the first step is to figure out those possible choices of X. What are those possible values that can be taken by X? So the question says, there's an insurance company and it offers its potential customers, clients, multiple different payment options. So X represents the number of months between two consecutive payments. So if you drive a car, you have to pay those insurance premiums, buy those, some of those options, and then choose what payment options you want to go with. You either make the payment every month, then the number of months between two consecutive payments is gonna be 1. Because you pay in January, then wait until February and make the second payment. So the interval between those two payments is just 1 month. So X becomes what? If your payment frequency is the highest. There's nothing like less than 1. You cannot make payments like every 30 days, every 15 days or something. The lowest, the interval, smallest interval between two consecutive payments is 1 month, 30 days. If you make a payment in January, the next earliest possible payment time is going to be February. If you want to make less frequent payments, you can choose the option of, say, every 3 months. So if you pay now, the next payment time is going to come in April. Number of months between those two consecutive payments is going to be 3. Or 4, if you want to prefer to make it, to break it into 3 and then just to make 3 payments per year. Or 6, but nothing bigger than 12 because you have to pay something every year. You cannot pay go without paying anything like 2 years and then pay everything else. Nothing like that. So the highest frequency is a monthly pay, make one payment per month, and the lowest frequency, just an annual payment. You just wait one time, pay everything, done with the entire year, and then go to the next year. So that's what this X represents. You make a pay, and then until the second payment, what's the number of months in between? So it could be 1. The smallest number taken up by this X is obviously 1. How do we know it? No probability mass for some value less than 1. That's why we know it. So if that's a PMF, because that's why we want to construct. So there must be some specific values that can be taken by X, and say that there's a minimum value somewhere here. Minimum X. We don't know what the number is now, but we'll assume that there must be some minimum. Presumably 1. If the value is less than 1, and if you plug that number into CDF, what do you get? Because the CDF is, if you plug in A, it means that probability such that this variable X either equal to or less than A. But that's the minimum value there. But if you plug something smaller than that, what's the value for this? Nothing. It doesn't happen because it's even smaller than the minimum value. So that's why you keep getting this 0 for anything below that, anything less than 1, which means that there's nothing before 1. So minimum value for this variable X is 1. Because when it becomes 1, see that this includes 1, so you have to look at the second interval. There's a suddenly jump in this probability, which means that there's a probability mass of 0.3 at this point. So that's now 1. So the minimum value that can be taken by X is 1, and then there's a mass, probability mass, jump, and size of that jump is 0.3. Look at the second subinterval, either equal to 1 or bigger than 1 but strictly less than 3. Probability mass stays at 0.3. No change whatsoever. And then you go all the way to 3. So the fact that the CDF value doesn't change at all between 1 and 3 means what? Can take any value between 1 and 3? No. If we can take some value between these two, what happens? CDF should increase, but it stays same. Fixed at the value 0.3, which means that there's nothing in between. Next jump in this CDF comes when x becomes 3. Same at 0.3 all the way up to 3, but if x becomes exactly 3, which is this one, there's a jump from 0.3 to 0.4. So size of jump is 0.1. That's the probability mass at the next choice. So the pattern here, if it's a valid CDF, these are sub-intervals, smaller intervals, must include the strict equality on the left-hand side. But equality on the right-hand side becomes strict equality. No inequality there, because there's a jump. And size of the jump, which is nothing but the probability mass, is the difference between the previous CDF and this CDF. So always see that the equality must be on the left-hand side. That's where the jump occurs, which means that there is some positive probability mass. And that value of probability mass is nothing but the difference between those CDF value between the interval before and the interval now. So if you use the information, easily construct a PMF for this X thing. Should be this. You just repeat what I'm doing here. So the mass for the first smallest one for X, smallest possible one for X, which is 1. There's a sudden jump in the probability mass of 0.3. And the next possible value by taken by X is 3. And there's another jump of smaller one, 0.1. And then even smaller jump for the next one at 4. And gets bigger to, increases to 0.15 at 6. And biggest jump at the last maximum possible value taken up by this X thing, which is 12. You have to make a payment at least once a year. So the number of months between those two back-to-back payments cannot be bigger than 12. Must stop at 12. Nothing after that. And again, if you want to make sure, double check that you did everything correct. Those figure the probability for each one of these possible outcomes for X must add up to 0. And if you add these numbers up, you indeed come up with 1. So that you know that you're on the right track. So again, given the CDF, construction of the PMF is trickier than the other way around. If you given this PMF, construction of CDF is very straightforward. But given this, coming up with tables like this one, this 30 mode, you have to think a lot. And then the way to do it, pay attention to the fact that the equalities are included by this left-hand side, and that's where the jump occurs. And jump in the probability means just there's some non-zero positive probability mass at that specific point. So first to figure out where those jumps occur. First jump comes at x equals 1. Second jump comes at x equals 3. 4, 6, and 12. Those are the possible values taken by x's. And then each one of these corresponding probability mass for each one of these x's, nothing but the size of jump from moving one subinterval to the next subinterval. Just subtract or get the difference between these two consecutive numbers under the CDF. That's the trick. Okay. Second one, using this information, compute these two probabilities. So number of months between two back-to-back payments equal to or bigger than 3, but less than or equal to 6. That's the first probability of our interest. Second probability to figure out is it's either equal to or bigger than 4. You can either use the CDF or PMF. Answer should be the same. That's what's important. But probably it's easier to use the PMF. So since this one's simple, let's do it now together. So first go for this first probability. See that the only includes like x equals 3, 4, and 6. But then we constructed a PMF function. Just add up those corresponding probability for each, and then figure out this entire probability. And similarly, you can figure out the answer to the second probability. So if you do everything correct, you should get something like this. Here I use the PMF, a CDF function. But you can, equally likely to use the PMF and then still get the same answer, 0.3 and 0.6. Last one before we move over to expected value, which is next topic. This one is a bit tedious. I mean, it's not that difficult, but you just have to count over. So the situation is that you're given two fair dice. One die and second die, you just roll them together. Assume that those outcomes from those two different dice are completely independent. Outcome from the first die doesn't depend on that from the second one. And then knowing that, define random variable m and define it to be the maximum value out of the two. So if you get 3 from the first die and 6 from the second die, m becomes 6, the bigger number between those two. And then the first one asks us to construct a PMF table. So what are those possible values that m can take on? M can be 1, can be 2, can be 3, 4, 5, and 6. Those 6 are possible values taken by this m. You just need to figure out what's each corresponding probability. Starting from the smallest one. What is this probability? M is the max value out of those two outcomes. You only take the maximum, biggest one. And the chances that M is 1 is what? You roll 2 dice, observe those outcomes. You're interested in the case that M equals 1. What's the possibility? Or, yeah, exactly. So the outcome, only possible outcome for this one is 1, 1. What about M equals 2? You sure? So it could be 1 and 2, or the opposite case, 2 and 1, or could be 2 and 2. So 3 of them. So you just have to tediously count each one of these possible outcomes. But if you do it correct, you should get something like this. So we did it up to here. Then if you continue with the case m equals 3, it's either 1, 3, 2, 3, 3, 1, and 3, 2, and 3, 3. That's a 5 out of 36. I omitted those details for the last 3, but you can check them and the answer should be the same if you do it correct. Only shows it up to like a first 3, and then it becomes more tedious because the number of outcomes, possible cases increase to 7, 9, and 11 for the last one. Right. All right. Next one. Given this PMF, now you have to construct a CDF and graph it, which is the exact opposite of the previous exercise. Given the CDF and you were supposed to construct a PMF, now you're given the PMF from the previous part and then go on to construct the CDF. Same information can be used, and if you do everything correct, you should get this one. So again, the two important characteristics of the CDF function, so those subintervals must include equality on the left-hand side. So equality all the way on the here, right, left. The last one, you can just take the mirror image of this, put 6 on the left, and the direction of inequality will switch from left to right. So what I'm saying is, I don't know why I write it this way here, but you can just write this, which is the same as that. Okay. And then the place where these equalities are placed are all on the left-hand side. And then there's a sudden jump, and size of the jump between these intervals from 0 to 1 over 36, that's nothing but the PMF value that we just constructed. Right? And size of the jump from the second and the third is a 3 over 36, and that's the probability mass for the second outcome, which is 2. And similarly, the size of the jump between this third one and the fourth is 5 over 36, and that's the value under the choice after that one, which is m equals 3, and so on. And if you do everything correct, at the end of the day, so if you accumulate every possible choices taken by this m, they all should add up to 1. Then you know that this is a valid CDF. Okay. So it can be either way. I give you the CDF and ask you to construct the PMF, or the other way, give you the PMF and ask you to construct the CDF. Last year, I think I provided with the PDF, PMF, and then compute some relevant probabilities, and then construct a CDF. So this time I might switch the order, and do it the opposite way. Either way can be tried. The same information can be given using this graph, step function. So constant for certain interval. So this is CDF. Whether you put it this way or put it this way is exactly the same. But here specifically it's being asked to construct a CDF using this graph. Graph it. So you have to graph. So the right shape of any CDF should be like a step function. Constant for a certain interval, there's a sudden jump, and then constant for some time. There's another second jump, and then constant for a while, and then the third jump, and then constant for a while, and so forth. It's like a step when you move over to those stairs. Of course, those size of jumps represent the size of those PMF function. Right? Next week, bring the next lecture note. I think we can finish it by like sometime on Monday, certainly before the end of the Monday's class. We move over to the what's coming up next. I forgot what it is. Is it discrete random variable? Like a Bernoulli binomial, that stuff? So lecture note number 6 should be ready when you come back next week. And plus the quiz. Right. Now we move over to the next topic, which is another very important definition, expected value. So imagine that there's a distribution, it's a smooth curve. We don't know the specific characteristics of this one, so we need to figure it out. Usually the first thing that people try to figure out where's the highest frequency, center value, and this value is represented by this so-called expectation. So you see that this E of x thing, it's just a number. But unfortunately, we don't observe it, so we have to guess it. But then once we estimate this unknown number, what we do is just we try to match this with this underlying distribution, so that's basically this question mark. Computed one there. Center value. Center of certain distribution. So expectation of it, or expected value of it. Notation is just a Roman E, and then parentheses, whatever random variable might be inside, close it, and that becomes the center value, middle value. Something like a median, but not quite the same. How do you compute this one? Use the PMF. The same PMF that we have been dealing with today's class. First, figure out all those possible values taken by x, the first x1, all the way to the very last xn. So using those each corresponding probabilities, which is nothing but the PMF, multiply that probability by those realized values, and then add them all up. That's expected value. So if you go back to any of those PMF table, one of them was this one. So given this x potential outcomes, corresponding probabilities, which make up the entire PMF, first get the product of these two, save it, get the second product, third, fourth, and fifth, and add them all up. That becomes your expected value. That's how simple as it is. What does that represent? Middle value. Ballpark, if you just ask what's the most likely value taken by X, that's expected value. Because that's in the middle of it. If you just close your eyes, then randomly pick any value that can be taken by this distribution, most likely to be somewhere in the middle. So that's expected value. If you compare this one with the sample mean, so I said that this number will be most likely never known to us, so we have to estimate it. Simplest possible way to estimate this one is simply take the sample mean of it. If you recall the definition of sample mean, first class, first week. Sample mean, x bar on top of it, x1 times 1 over n, which is the sample size. Second x times the sample size, 1 over sample size, all the way to the very last x, and 1 over n. That was the definition of sample mean. If you compare this definition and then put it aside, the definition of the expected value, you see that there's a close analogy.